So what is the next in AI? What will happen? What will be the new advances? This is something you can, a question you can hear everywhere. You have this in a newspaper each day. And I suppose that no one, maybe one of these four guys, is able to say what will happen in 10 or 20 or 30 years. But what will happen tomorrow is probably something that is now in labs, that is current research. And we are fortunate to have these four brilliant researchers to tell us what they are doing now. And I will first ask them to briefly introduce them, but I'm not sure it's very useful. And then to say us a few words about what is their work, today work in research, what are they doing, what are they doing with PhD students and with company maybe. So maybe Francis, you can start.
So thank you, Isabelle. So I'm Francis Bach. I'm a researcher at Inria. I'm leading a team joined with Ecole, normale, supérieure and CNRS. And what we're currently doing, we have many activities, but we focus mostly on 3 fronts. The first one is uncertainty quantification, excuse me, which is to me the, oh, sorry, okay, so I won't start again, so I'm Francis, hello. And so we work on 3 main fronts. The first one is uncertainty quantification, which I see as the elephant in the room when you apply those AI techniques in practice, in science and industry. It's not only useful to predict something, you have to predict the confidence about what you predict, and it's not, and the confidence has to be well calibrated. So there are many different techniques coming from statistics, and one of our aim is to relax the assumptions which are made to make those valid, and this is like quite a big area now in machine learning. The second front is a bit more technical. It's about like making reinforcement learning robust. So what is reinforcement learning? This is the engine behind all learning interactions, whether this is in robotics or when you do some reasoning tasks. And here it's fair to say that essentially it does not really work in the sense that if you try it on your own, it will fail. And there are several names for this, like collapses of various kinds. And there's a lot of trial and error being needed for all of that. It's a waste of resources, call it time, dollar, GPU, or carbon footprint. It's something which is still, like, I think, quite open. And final stream of research is about optimization. So those like few lines of code that you need to update your model as you see more data. And it's fair to say that a good algorithm will make or break a learning architecture, and you can gain a factor of 2 to 10 by having a better algorithm. Just those few lines of code, sometimes you change a few characters, and boom, you can get a factor of 2. And this is quite an active area in machine learning, and we are focusing on trying to understand what makes an algorithm better, both in terms of architectures and data type. And then it's not only a matter of who has the most number of GPUs. Thank you, Francis. I will ask all of you, but if you have any reaction, you can interrupt as you want. If everybody agrees, it will not be so funny, but I'm pretty sure that it will come later. So you can, okay.
I can say, can continue on what Francis said. I'm against purely GPU-based research.
Thank you, Jean. So maybe next one, Yann, do you want to say us a few words?
Yeah, I don't disagree with Francis. Not surprisingly. Those are very useful aspects of AI and machine learning. What I'm focusing on, though, is AI systems that understand the real world. So I'm sure you're not surprised to hear me say this. But we have techniques that are really good at dealing with sequences of discrete symbols, predicting the next token in text or in code or something like that, and even doing some level of planning. So whenever a data is representable as a discrete sequence of symbols, things like LLMs and GPT architectures work really well. Of course, there are specialized techniques for handling things like video and images, audio. But what works best for understanding images or video are architectures that are not generative, architectures that basically learn a good representation of the input signal that allows it to make prediction by eliminating all of the details in the signal that are not predictable. So Francis was talking about predicting uncertainty. If you're trying to predict what's going to happen next in a video, there's so many plausible futures that parameterizing the set of plausible futures is basically intractable. And so the best way to handle this is to abstract away a lot of details that happen in video and then make predictions that you can actually make, even if there is still a little bit of uncertainty left. So that's the whole idea of what I've called JEPA, Joint Embedding Predictive Architecture, that Jean and I actually have been working on this together with a bunch of students. And this is, I think, a good mechanism by which to build world models. In other words, if you have some idea of the state of the world at time t, and an idea of some action or intervention you want to make, can you predict the state of the world at time t plus 1? And when I say world, I don't mean the entire world. I mean whatever system you're trying to control or whatever environment a intelligent system is evolving in. And so if you have a system that can make this kind of prediction, that it can predict the outcome of a sequence of actions. And if that's the case, then the system can figure out an optimal sequence of actions to accomplish a task, to arrive at a particular goal. And this is really, one of the processes by which intelligent behavior emerges. You're able to predict the consequences of your action, and that allows you to plan a sequence of actions to arrive at a particular goal. We do this all the time as humans. Animals do this too. Current AI systems, the ones that are autoregressive, don't do it. So that's kind of the next frontier. What I'm foreseeing is that it's going to bring about a new revolution in AI and open the door to a lot of applications in the real world of AI systems, and sort of bridge the gap between the fact that we have systems that can pass the bar exam and get good scores at international math Olympiads, but we still don't have domestic robots, so we don't even have robots that are as agile as a cat. And it's not because of the mechanics, it's because we can't make them smart enough for that. So that's my plan.
Thank you. Any reaction, or we give the floor to Stéphane? Please.
So the goal, the kind of research, first of all, I'm Stéphane Mallat. I'm an applied mathematician working at Collège de France. And we've been absolutely amazed by the results achieved by neural networks since basically 2010, when they began to be very efficient on image classification, and then came LLM. But basically, we don't understand from a mathematical standpoint why these performances are possible. They are achieving incredibly complex tasks. There is an exponential explosion of possibilities. The fact that they are able to achieve accurate classification, that they can do generation, means that somewhere they captured the structure of the problem. Now, in neural network, it's all about computing conditional probabilities. And these conditional probabilities are incredibly complex. What are the mathematics that allow you to compute them, estimate them from somewhat limited set of examples? Now, this connects very deeply with physics, because the same kind of question is asked in statistical physics. Understanding the probability distribution of physical events is about understanding how you can capture the energy, and therefore understand all the interaction, basically understand the physics. And in fact, these neural networks have been very efficient nowadays, for example, to compute the weather in the next day. In other words, to be able to compute the evolution of physical systems. So the question is, how come this is possible? What are the mathematical structures? And during the last 3-4 years, things have been moving a lot. One of the very important elements was these ideas of transports, these ideas of score diffusion algorithm that led to the spectacular generative AI for image processing. And what basically they do is they try to look at the evolution of these probabilities along a regular path and realize that the transition probabilities are somewhat easier to compute than the overall probability distributions. So understanding these phenomena is, of course, absolutely key, not just for this generation, but also to understand physics, because these kind of probability distribution can describe the evolution of the physics. So understanding the math is one of the big aspects, and these slicing of probabilities on which I'm working. Now, the other aspect, you mentioned collaboration with companies. I'm collaborating probably with the biggest European companies, maybe besides the Russian army, which is called the Éducation Nationale, 1 million people. And this is a company which is very deeply shaken by AI. Why? Because all kids are now doing their homeworks with AI. You can't give, if you are a professor, your any homework now to your kids. And also the kids are wondering, why should I learn all this given that my chat GPT can answer all these exercises? So understanding how to work with AI, understanding how to reorient education in order to provide an education which is able to work, have a critical look at AI, but also complement, is one of the deepest questions, I believe, right nowadays of our society, because education is really about the future, and it's about the tension that we are seeing even in the political arena. So that's, for me, a very fundamental question on which I'm working with a group between Ecole normale supérieure and Collège de France by trying to do experiments in class, in particular in mathematics, and see how we can address this kind of question and how we can use AI to help mathematics teaching, especially given the fact that we are in a very deep crisis of mathematics teaching. You've probably heard about France being nowadays one of the last country in all the international evaluations for collège and lycée. Beautiful research question and very high impact question.
Thank you. Francis wants to answer.
Yeah, so I agree with Stéphane, and I would go even further. You mentioned like Éducation Nationale, so up to high school. Even at the university level, engineering schools, many of the tasks that we ask students can be done by AI, okay, more or less well, and often very well. And we're in a situation where all the tasks that we ask students to train them to do a higher level task are not being automated. And it's true for education. It's also true for many other parts of life where AI can be used. How do we train people to do things that are needed to be done for the next level of tasks? And I don't have any answer. It's a key issue that I see appearing even now. I have master students. Why should I have them work on something which I know could be done more or less with me interacting with ChatGPT? I'm doing it to train them to solve better problems. But unless we solve this in a good way, and I don't know the good way, I think we are in a deep trouble in the moving forward.
Be careful, there are probably some of your master students in the room.
I didn't say PhD students, so the PhDs are safe, but master students maybe are not safe.
So, Jean? Oh,
No, go ahead, go ahead.
you want
I was just saying it's a good argument to do a PhD.
Okay. Jean?
Okay, so I'm Jean Ponce. I'm a professor at UNSPSL and also at New York University. I'm a computer vision person, but I dabble a bit in machine learning, robotics, and image processing. I spent most of my career looking at rather abstract problems in geometric foundations of vision, even recently trying to understand some of the algorithms people use in self-supervised learning for Yann models. But I've been interested for at least 10 years in interdisciplinary work and applications, and I think this is, I'm not a futurologist, I cannot tell you what's the future of AI, I have no idea. But I think this is a very important area of AI. So I do quite a bit of work in AI for the hard sciences. So I work on this with Julien Méral, with a colleague of mine, a former student of Francis and mine, who is now director of research at Inria and RIE AI in Grenoble. And we work on two topics. The first one is astronomy. We work with Anne-Marie Lagrange at Observatoire and Maud Langlois and Olivier Flasser at CRAL in Lyon on the detection of exoplanets. So why would we want to do that? Because those are new problems, new data. There's an important impact. So imagine we find plenty of new exoplanets and we do direct imaging, which means you can observe directly the atmosphere of the planets, and you find biomarkers such as water vapor in the atmosphere of these planets. That's a big deal. But also it's important with challenges. We don't have ground truth data for these kind of things, kind of false negatives, etc. So we work on that. We also work on microscopy, again with Julien. Also, I forgot to mention our student Théo Bedrito for the astronomy, but with Julien and our student Romain Seaille, and with Jean-Baptiste Masson from Institut Pasteur, you have heard earlier, on molecular microscopy. So here the idea is that you have an organic tissue, a living organic tissue maybe, and you shine laser light on it, and you have dropped on the tissue molecules that are called fluorophores that fluoresce under laser light, and you want to localize these things in space in 3 dimensions so that you can measure the tissue with precision better to the limit of diffraction and study deeply these organic tissues. Again, this is very interesting. You get to meet people who are really interesting. You get to learn a lot about optics. You get to use sophisticated methods, both in astronomy and microscopy, sophisticated models of the optics. We know everything about the telescope. We know everything about the microscope, and this is very interesting. This goes beyond the hard sciences. I worked for about 10 years with Hélène Dessal at the NSPSL and with Yves Bellman at Ecole on Pompeii. The idea was to use computer vision and photogrammetry to make some kind of 4D database of a villa outside the walls of Pompeii called Villa of the Diomedes. Again, you get to meet wonderful people to work on interesting things, and this resulted in a beautiful book. And so recently we have worked as well on trying to detect looted sites in Afghanistan in satellite imagery, again with Yves Bellman, but also Mathieu Aubry from ENPC. And recently we have started talking with artists like Samuel Bianchini, and we hope we will do things together. So this is on the science side, I'm almost done, but also do engineering. For example, we do a CFRE thesis with François Gardère, student, and Camille Gauthier at Louis Vuitton, which is not an obvious choice for AI, right? And Chizé Chen, one of my colleagues at Prairie and Inria, and this is about how to use AI to indirectly select garments on a website. And finally, we also do image processing, and I've created with Julien and our former PhD student Bruno Lecoy a startup called Enhance Lab that develops image processing technology that improves the resolution of regular images by a factor of 4, with applications going from defense and surveillance to medical imaging, for example. So I think this is one of the real frontiers of AI, is how we can use the technology we do in a creative way with science and engineering.
Thank you. This is what we call today AI for sciences. So does anyone want to react on this? I think you have also works in maybe chemical, no?
Well, yeah, I mean, AI for science is a huge field nowadays. I was saying AI for science is an absolutely huge field nowadays to produce new material, new molecules in a medicine. I mentioned physics and also mathematics, if mathematics can be considered as a science. But we may speak about it on thinking what's next, what's the implication of this in all these fields. This will probably require also an adaptation of this field, but we may speak about it afterwards.
Thank you. So another topic that is supposed to be a hot topic is robotics. And Yann, you already mentioned something about physics and so on, the physical world. Do you believe that robotics will be a hot topic in the following years?
Well, it's already a hot topic, but mostly at the sort of electromechanical level. There's a lot of companies that are building various types of robots, but humanoid robot is kind of a more recent phenomenon, and there's a whole bunch of them popping up everywhere. Now the big secret, which some of you may have heard me say in the past, is that absolutely none of those companies has any idea how to make those robots smart enough to be useful. Because the techniques that are used at the moment to train a robot to do something is a combination of collecting a lot of data from human experts or human operators, and then training the robot to basically clone the behavior of humans. So that requires a lot of data collection. That requires, training. And then that requires fine-tuning in simulation, generally. And simulation doesn't work for everything. It works for locomotion, doesn't really work for manipulation, at least not well enough. And so there's a lot of kind of fine-tuning to do in the real system, and that takes a huge amount of time. And so the question is, how do we bridge the gap between the time it takes for humans or animals to learn physical tasks versus the time it takes to train those systems to do any particular task? There's still orders of magnitude of difference, and we need to bridge that gap. My bet is on this idea of world models and planning, but this is still to be worked on. So what you're going to see over the next small number of years is that whatever applications of complex robots are going to pop up are going to be for relatively narrow tasks for which it's economically feasible to collect lots of data. But you're not going to have general purpose domestic robots anytime soon, because that will require a new revolution in the way we handle AI, essentially, and have systems that understand the physical world that I was talking about previously. So that next revolution in AI is coming. It's not clear how long it's going to take. Could be 3, 5, 10 years. And we're not going to have domestic robots and level 5 self-driving cars that are completely reliable until that happens. Those are kind of AI complete problems, if you want. But that's what I'm focusing on. That's what my new company is also focusing on.
Yes.
So I don't quite agree with. I mean, I'm completely agreed that domestic robots are not around the corner. Robots are dangerous. If you want a robot to be able to carry an elderly person, carry 50 kilos, that robot can kill you. Okay, so we have to develop real safety measures for robots. It's important. Also, of course, learning will be important for robotics, but robots are devices that we build. Okay, so we know their dynamics, we know their kinematics, we know a lot about them. We can model a lot of things about them. There are some other factors that are interesting. There's a democratization of robotics happening right now, in particular with the advent of the unitary robots, for example. You can now buy a dog robot for about $5,000, maybe less, and a humanoid for about 20,000. That means, and you can also go to the deep learning store and buy the latest library of reinforcement learning. That means that any lab, pretty much anybody can afford these robots, can do a starter kit where they will get a robot moving without much knowledge, without much resources. And it will be interesting to see where the democratization takes us. There's a lot of robot people now who have never known anything about robotics, and still they play with robots. So where will it go? It will be interesting to see. And I had one last thing, but I forget because you are grimacing at me. Last thing. I cannot talk about the future. I still think that robotics will have to play a huge role because it's an integrating field. An AI that drives a robot needs to perceive, needs to act, needs to navigate, needs to manipulate, needs to plan. And all of these have to work together. On top of that, you have scientific challenges, such as, for example, creating and breaking contacts. These create discontinuities in the physical process that are hard to manage with machine learning.
So short comment here. Yes, we do build the robots, and we can write the equations that model the dynamics of the robot. As long as the robot does not interact with the real world, or at least only interacts in simple ways, like the feet on the ground. So, which is why you see those impressive videos of robots kind of doing somersaults and doing all kinds of stuff. But that's all pre-planned, and it's planned from a mathematical model of the robot. Some of it is fine-tuned with reinforcement learning or system identification. The difficulty is how you do something in the world, how you act in the world. There's just grabbing an object and pouring water in a glass. that's relatively simple. You can train a robot to do this relatively reliably. But like in general term, have the system really have an intuition for what happens in the world? That's where things don't work anymore. So that's going to take a while. That's really the purpose of understanding the real world at the sort of intuitive level.
So thank you. To go to another topic that is often discussed in other assembly, we also talk a lot about the consumption, energy consumption of all these AI models. And it's not the case of all the models. And I know that, for example, Francis, you are very careful in what will come in the next future.
Yeah, so I am careful. So I think we can't avoid really to have lots of data to learn about the world, whether it's text or word models. I think we can't escape this aspect of things, but to me there are two buts. The first one is about all those tasks where there are not enough data to do massive data from scratch, and I think about robotics as being one of them. You can have armies of people labeling things. It will never be scalable for robotics. Okay, this is something for healthcare. There are a lot of big databases, but there are many problems where there's simply not enough data to reproduce what has been done on text. So this is the first but. There are many tasks on which data is not only the issue, and you need to have better ways of doing learning more efficiently. And the second but is, even for the very large problems where you want to learn the entire web, clearly you have to read the data, but there's no impossibility of having cheaper models which can run on less than hundreds of GPUs. And this is still totally open in terms of theory and practice. Okay, how do we do learning efficiently, both in terms of call it time, call it energy, call it carbon footprint. At the end, it is too costly and it's not scalable in the long run. And that's why I think research is key to develop new areas. And it's not only research for the next 6 months. Okay, this is long-term research, and it's one of the reasons why I'm so happy in academia at Inria, ENS, and CNRS, because we can pursue this agenda. And I believe that this is really one of the issues that I see in modern AI is the focus really on short term and forgetting that longer term, just like putting more GPUs is not scalable for various reasons.
Let's come back to maybe just Stéphane, 2 minutes, because let's come back to what you talked about previously about mathematics and the importance of all these fundamental notions.
Yes, and that is in fact aligned with what has been said. If I was to say what is going to be also a fundamental research issue of the coming years is just the word understanding. Understanding, I mentioned about understanding how things happen inside neural networks, but if you think, for example, on problems such as climatology, where people want to use AI and are trying to use AI, well, you don't have enough data. So you need to incorporate physics within the model, which is what Jean mentioned in the case of robotics, but understanding how to incorporate physics within deep network, which have a very different language in some sense to process the data, requires to understand how they work inside and how to interface the two aspects. So working with very limited amount of data, which can happen also, for example, in medicine or physics, requires understanding. Reversely, one question is to push the level of understanding of deep networks. So let me speak about what's happening, for example, in mathematics. In the last 1 year, the level of mathematical systems have improved in an amazing way. And as you mentioned now, you have the golden medal of the Olympiad obtained by such a system. But essentially everybody agrees that they can produce on a fixed set of questions a solution, but cannot pose the problem because they don't have a wider understanding of mathematics, of what it means, what the proof means. In other words, the semantic element of the map. So from there you have two views. The optimistic view, like what Tao would think, is, well, these tools are just assistant that will help you to do better math and to be more efficient, but yourself, you have not to act as a technician, but develop your ability to have a deeper understanding of the field. But there are more pessimistic view, like the one, for example, of Gowers, saying, well, this system do already have some level of intuition through the calculation of probabilities of the results. We cannot really say that they won't get these deeper understanding. So this is not just an assistant, it's a total revolution of the field, and it's not clear whether they will not reach that level that we do have currently in mathematics. So understanding is very fundamental, and it's one of the elements that, in some sense, deep networks don't have on abstract problem. On the other hand, do we really want to advance this line of research if you are a mathematician? Not absolutely clear, because you are really creating a system that can be better than yourself. So in terms of pure intellectual research, I think it's a fundamental issue, and it will have huge applications in physics, in many areas. The day it will have it, it's going to be a challenge for ourselves.
So Yann wanted to react.
Right. Nobody answered your question about energy. You can. So first, I'm not going to answer that question, but comment on what Francis said, which I think is important. And I'll use an example. We have millions of hours, literally millions of hours, of cars being driven by people, okay, where we have all the sensor inputs from the cars and the controls, pedal and wheels. Despite that, we don't have level 5 self-driving cars. And so the idea that somehow you can train a reliable system by imitation learning, by just trying to clone the behavior of a bunch of humans, works to some level, but if you need the type of reliability that is required for autonomous driving, it simply doesn't work. The scaling laws just don't work. You can increase the amount of training data as much as you want. There are always going to be corner cases where the system has not been trained and is going to do something really stupid. And so, in my opinion, the solution to this is to get some inspiration from the fact that a 17-year-old can learn to drive a car in about 10 or 20 hours of practice, largely without causing any accident. And so that tells you that, of course, the 17-year-old has had 17 years to learn how the world works, right? Has a mental model of what happens, can predict that if the car is driving next to a cliff, and if you turn the wheel to the right, the car will run off the cliff and nothing good will come out of that. You don't have to try to know what's going to happen. And so this idea that you can predict what's going to happen as a consequence of your actions, which is really behind this concept of world model, is probably one of the things that will enable things like level 5 self-driving car without cheating. What I mean cheating is companies like Waymo, which use all kinds of sensors, and where the car can call home when it's stuck in a bad situation, and they have armies of engineers kind of treating all the corner cases. So that gap again that we need to bridge between having millions of hours of training data and not being able to have a car that drives itself, as well as a 17-year-old that has practiced for 20 hours. Now about the question of energy. This is not a real question. Yes, AI systems consume a lot of energy, particularly for inference. If we need to serve billions of users to use their AI assistant that is going to be with them at all times, it's going to require a lot of computation. When all is said and done, it's only a few percent actually of all the energies consumed in the world. May seem like a lot, but it's actually not enormous. And it also saves energy because you replace activities that you would otherwise do that would require more energy, like traveling. So that's the first point. Second point is the incentives are there for the industry to minimize the amount of energy consumed as much as possible. And that goes everywhere from fabrication technology, smaller devices, to chip design, more efficient memory design, so you don't have to shuffle data all the time, which is really what GPUs are, to architectures and algorithms, to underlying arithmetics. People are kind of innovating as at the type of arithmetics you have to use to run neural nets, very low precision, to algorithms, to architectures, to distillation, to all kinds of stuff, to mixture of experts, so you don't have to run big neural nets all the time. The incentives are there because that's what costs money. To measure the capacity of data center today, you don't measure it in exaflop or whatever, you measure it in megawatts. This is what people are trying to maximize everywhere across the industry. We don't need new incentives for this. We do need research.
Yeah, I wanted to say something about energy, so I have no idea how to solve it. Yann knows, but I don't. But I can give you examples where it's important. So we do stuff where we have a image processing thing running on the phone. You cannot have something that's going to drain the phone battery in half an hour. If you want an autonomous car, you don't want your intelligence system to consume more than the air conditioning of the car. It just won't work. So these issues are truly important. Now, for the fact of, I don't know, in France you cannot get your driver's license at 17. You have to try it 20 times and it costs a fortune.
It is 17 now.
But also, more seriously, on the thing that you can just observe the world and everything will work. There is a very interesting blog. There is a famous robotics guy called Rod Brooks. He's like me, he's an old guy. So maybe he sounds like an old, I won't say the word, but he has an interesting blog about the view of robotics. You film enough people doing stuff, you film enough robots doing stuff, maybe it won't work. And he has a video in this where a person has their fingertips anesthetized. And the person is trying to pick up, this person like you and me, perfectly normal person, but fingertips anesthetized. He's trying to pick up a match and scratch the match. He will never, he doesn't manage to do it because the visual data is not enough. You need your tactile data. And tasks like manipulation are very, very hard. They are much harder than navigation. And hoping to do manipulation by just observing people, maybe a pipe dream.
Francis, yes.
Okay, so you asked for disagreements. So we disagree a bit with Yann. So I agree with the fact that incentives are there to reduce the cost. But I still do think that the energy overall, it's not like an unlimited resource. So if you have one activity, AI, that grows double every 6 months, at one point it will become, it will saturate all the new energy potential.
No, because you won't have the revenue to fund this. Nobody will pay for that. So it's limited by how much people are willing to pay.
Yeah, but still, at the end, you're still going to the curve is not in your favor. The curve is like doubling every 6 months or every year.
No, it's not possible because in the end you have to get people to pay for it. And so if you ask people to pay for $1,000 a year to use an AI assistant, are they going to pay for that?
To jump into the conversation.
Let me jump in. I would like to jump in into a topic, and that's relatively to what Yann was also saying, is this notion of world model, which is in some sense very much related to this notion of understanding that I was mentioning. I think it's important also to remember that in the 90s, in the old AI, people began with trying to build world models. They began to try to understand how we do it. Oh, we extract edges, we find the contour of eyes. So that's probably how a computer system must do it. And that was a big failure. So the ability of building a world model, so from what we think is a world model, was a failure. The remarkable success of AI, in some sense, and machine learning, was at one point to forget about world model and to try to see these models emerge from the complexity of the data because of this ability to build, to achieve complex tasks, and therefore understand how to structure internally the information. So the big challenge is about this notion of world model. Can we put it? Should we orient the system in order to build this world model, which was a difficulty in the past? Or should it emerge the way it has been happening in the last 15 years of success of AI? I think that's an important question.
Yeah, the question is whether we can replace writing down a bunch of equations to kind of model a phenomenon that we observe by data-driven, training a model in a data-driven way. That's, and I agree with that, of course.
Any other reaction? No?
Of course, you should still write the equations when they're available. It would be really foolish not to do it. When you have good models, use them. They are, of course, the models are always imperfect, but again, I gave you a specific practical examples. Telescope and microscope, you know exactly the optics, and if you are not going to use it when you can actually model it and measure it in real time, then you are losing big. And empirically, we have shown that all things that use the models are better than pure deep learning-based methods.
I'm glad you raised this point, because it depends what equations you're writing. In principle, there is an equation, a single equation, or like a small number of equations that can explain everything that's taking place in this room right now. It's quantum field theory. But there's absolutely no way you can use those equations to describe in interesting ways what happens in this room. What happens in this room is best described at the level of psychology and some notion of science and whatever. And so we invent abstractions that allow us to describe a particular situation without taking into account all the details that are irrelevant. Instead of quantum field theory, we can have particle physics, we can have atomic physics, and molecules, chemistry, biochemistry in the living world, and organelles and cells and organisms and blah, blah, blah. And every level in this hierarchy is a different description of the phenomenon that we observe that allows us to make different types of prediction. This idea that you need to find an abstract representation that allows you to make prediction is absolutely key to understanding the world, and that's what the JEPA stuff that I'm working on for world model is based on. Learn a representation of the world that allows you to make predictions. Writing equations just puts you at one particular level, and it might not be the optimal way for planning or understanding.
Thank you. We are now close to the end, so I will just ask you as a conclusion, because to come back to the title of the table, what's next? What will be your next result, something that you would like to obtain in, I don't know, 1 year, 2 years, if we give you all the capability you need?
Thanks to you, I already have all the capabilities that I want. So my dream, I don't know, maybe like it's going to be technical, but replace AGD at last.
I'll vote for that. So I'm actually building a company, right? AMI Labs, and the whole idea of this company is to actually kind of build intelligent system of the next generation around this idea of world model and planning and dealing with the real world. So I'm hoping we'll make significant progress over the next year and perhaps have practical applications in industry fairly soon.
For me, it would be about understanding better the hierarchical structures that allow to considerably simplify these problems which are so complex. So that's one of an important ideas in all fields. Things, and Yann mentioned, things are have somewhat a simple way to be described because, let's say, you can aggregate atoms to make molecules, which you can aggregate to get materials and so on. And right now, we have a lot of difficulties from a mathematical point of view to make the link between these notions which explain somewhat why things are not so complicated as expected and the way these deep networks work. Building the bridge, which is also very close to issues in physics, is my dream.
Yeah, I don't have any dream. I'm pretty happy camper. But I think that if you look at the so-called revolution of deep learning, it was driven, in my opinion, by two main factors, two things. One is convolutional nets invented by His Majesty here, and the other one is the transformers. Both are ideas. They are not just a bunch of 50 people putting their names together on a paper and hacking and tweaking stuff. Those are real ideas. In retrospect, these ideas are related to previous things and they are pretty simple, but they are real ideas. So I would like to see new ideas with new things as important as CNNs or transformers emerging.
So thank you. I will have a last question, and I hope you can answer. I hope you can answer all together. We have a lot of young people in the room, engineer, PhD students, and so on. Do you advise them to have a career in AI?
Yes.
Yes.
Yes, but learn stuff. Don't just tweak buttons.
Yes.
And Francis?
I have no choice, yes.
So So thank you very much for this.